Good morning, everyone. Thanks for joining us for Emission Reduction Alberta's Research in Action. We'll begin with a few remarks from our CEO, Steve McDonald.
Good morning, everyone. I am Steve McDonald, the CEO of Emissions Reduction Alberta. I'm so pleased to see there are nearly 200 folks registered for today's discussion. And this event is a great example of the work ERA does every day, helping to move promising ideas through Alberta's innovation pipeline. Over the course of the next 2 hours, we are bringing together some of the province's brightest researchers with industry and others in Alberta's innovation ecosystem. For those in industry, it's an opportunity to discover early stage innovative solutions. And for researchers, it's a chance for them to learn more about what is needed to advance their projects toward commercialization. But before I offer an overview of ERA, I wanted to share some very exciting news which we just released an hour ago. Today, our board chair, Dave Collier, announced Justin Reimer as ERA's next CEO. Justin will begin his work at ERA on June 6th, later next month. As some of you know, I've had the pleasure of serving as ERA's CEO for more than 6 years. And it's been a real honor and a pleasure to work with this extraordinary team. And while it was a difficult decision to leave this amazing organization, I'm looking forward to continuing my professional journey with a focus on the actions that will help Alberta, Canada, and the world meet our economic and environmental goals. Justin is currently the Assistant Deputy Minister, Alberta Region of Prairie's Economic Development Canada. He brings a wealth of innovation experience and deep networks across all levels of government and strong connections with ERA stakeholders. He's going to make a great leader for the ERA team and will take ERA's ambitions to even greater heights. But back to ERA. Since 2009, ERA has invested the proceeds from carbon pricing on large final emitters to reduce GHGs and strengthen the competitiveness of new and existing industries in Alberta. Our investments both improve the competitiveness of existing industries by lowering costs and improving environmental performance, and create opportunities for new businesses and continuing economic growth. While reducing GHG emissions is the core of what we do, our vision is anchored in the belief that success is measured in both economic and environmental terms. Our funding is from the carbon levy paid by those large final emitters who are required to reduce their GHG emissions to meet regulated targets under Alberta's climate change regulations. As you can see on this slide, since 2009, we've committed nearly $800 million toward 220 projects worth over $6.5 billion. We offer a clear line of sight from the carbon levy to investments in the technology solutions needed to help Alberta achieve emissions reductions and economic growth. We fund later stage technologies, which means we accelerate projects toward broader industry deployment and adoption by helping to de-risk those projects at the crucial pilot, demonstration, and scale-up stages of development. We're also very interested in the early stage innovation, which is why we are here today. As I mentioned earlier, ERA works hard to keep things moving through the innovation pipeline. And we can't do any of this without partners from across the innovation ecosystem. The trusted partners you see here, including post-secondary institutions such as the U of A and the U of C, are central to our success. These 13 organizations are critical to how we can keep advancing the innovation needed to reduce greenhouse gases and ultimately reach a net zero future. We're on tight timelines today, so I'll hand things over to Isabella Tarasco, ERA's Program Manager of Strategic Initiatives, to walk you through the rest of today's event. I hope you have a very successful morning. Isabella?
Thanks, Steve, and good morning, everyone. We've had such a great response to today's session. It's wonderful to see such wide representation of small, medium, and large organizations from so many industries, as well as from government and post-secondary institutions. Thanks to all of you for tuning in. As you can see on this slide and the next, we have a lot to cover today. will get through 8 presentations in less than 90 minutes. Each researcher will take about 5 minutes to tell you a bit about what they do before we move on to the next presenter. To keep things moving, we ask that you take note of anything you want to ask any of the presenters, and we will open things up after the presentations. We've left about 40 minutes for a Q&A session, which is designed to give everyone on the line the chance to find out more and also provide some feedback on what may be needed next to get the work we'll hear about today moving to implementation. As we go through these presentations, please put your questions in the Q&A function on the bottom of your screen. And with that, I will hand it over to our first researcher, Dr. Samir Mushriff from the University of Alberta. Samir, go ahead.
Thank you, Isabella. I would just like to request the remote control. If I can get it, Kristen. Okay, can you see the mouse moving? Okay, I hope I'm audible. Thank you very much for the introduction, Isabella. My name is Samir Mushriff, and I'm Associate Professor in Chemical and Materials Engineering at the U of A. Just to give a little background about myself, did my PhD from McGill University in Canada, then worked for a couple of years with the US Department of Energy Research Center in Delaware. And then I spent 6 years working in Singapore before coming to Alberta in 2018. So if I have to talk about my research in one line, what I would say is our research focuses on developing cheap, stable, active, and selective catalysts from earth-abundant metals. And how do we do that? What we do is we first learn from the more expensive noble metals, which do a fantastic job by simulating reaction mechanisms and pathways, and which we simulate on supercomputing clusters. And then we take that understanding and modify the cheaper metals like nickel, copper, iron to bring their performance to the same level as that of noble metals. And here you can see an example on the left-hand side. At the bottom, you can see nickel here and the modified nickel in that yellow oval, which we predicted and developed using supercomputing facilities and quantum mechanical simulations. And later, when we looked at the experiments on the left, you see this picture where catalyst is covered by all these carbon fibers, whereas the modified catalyst remains clean. And where do we apply these novel catalysts for different reactions? A few of them are listed here. One is tar reforming and bio-oil upgrading, where one of the major challenges with the catalyst is that they are not stable because of carbon formation, and we can modify those catalysts to avoid carbon formation. Additional challenge in bio-oil, which is very corrosive, is that you need to selectively remove oxygen without breaking the carbon-carbon bonds in bio-oil. And we are developing those catalysts that can selectively do the job without excessive requirement of hydrogen. The other area is CO2 reduction, hydrogenation of CO2, and methane dry reforming, where you combine the two greenhouse gases, CO2 and methane, to form a mixture of carbon monoxide and hydrogen, which is called as synthesis gas, which can be used in Fischer-Tropsch process to produce liquid fuels. Here, nickel is again a very popular catalyst, but suffers from deactivation because of carbon formation. And we developed a novel nickel-based catalyst with some modifications to nickel to avoid that carbon formation. And not only we developed the catalyst here in this piece of work, but we also simulated reaction level kinetics at operating temperatures and pressure to test the performance of this catalyst under reaction conditions, which can be quite high temperatures for this kind of reaction. And last but not the least is the CO2-free hydrogen production. When I say CO2-free, the reason I say it's CO2-free is you don't get carbon dioxide as a byproduct. But of course, if the energy that is needed to break methane to form hydrogen is coming, it has a CO2 penalty, then you can't really call it CO2-free strictly. But if it comes from renewables, then you can call it CO2-free. And here, one of the processes we are working on is a catalyst that is immersed in a molten medium, where the molten medium acts as an efficient heat transfer medium, and the catalyst does a job to break down methane into solid carbon and hydrogen. We have also developing a catalyst that can stop methane from completely decomposing to carbon, but stop at second dehydrogenation, and then it facilitates carbon-carbon coupling to form ethylene and hydrogen. So you don't get any carbon as a product, and ethylene, as we know, is a very important, one of the most produced bulk platform chemical. If you can go to next slide. So how this supports Alberta's emission reduction goals? Of course, clean hydrogen economy. Alberta is the largest hydrogen producer in Canada, with lots of interest by companies as well. But this hydrogen is produced via steam methane reforming. And the hydrogen production method that we are proposing or working on, or you can call it a turquoise hydrogen, if it is powered by renewable energy. And the important thing to note here is that the catalyst that we are working on can bring the operating temperature of this methane decomposition down by about 300 degrees Celsius. It can facilitate decentralized processing. And the other benefit is, if needed, this catalyst can be tuned to produce ethylene instead of solid carbon. The second is CO2 utilization, where we can utilize CO2 and make it react with natural gas to form syngas. And another promising technology that can bring down the operating temperature is tri-reforming. And the other area is the biomass processing and biofuels, where we are looking beyond bioethanol. And the problem here is that even the state-of-the-art technology today, if it produces bio-oil of a good quality, then the yield is only about 20%. If you take the yield to up to 70 to 80%, the quality of bio-oil is poor, it has a lot of oxygen. And what we can provide is a catalytic solution to remove oxygen selectively and take the quality of bio-oil to a much better level, less corrosive, more stable. Last slide, please. And in terms of scaling challenges, we are still working at a laboratory scale right now on these catalysts. The catalyst synthesis process, testing it with real world samples, and doing further modifications and developing mechanistic understanding of the process or reactions. The challenges are to be able to develop these catalysts at a larger scale and then check the process level feasibility and techno-economic analysis. The next slide. And what we are expecting is some funding and collaboration to take our work to the next technology readiness level. In addition, what I would like to say is we are also looking for opportunities to work in industry to solve the industry problems. With the expertise that we have in developing reaction mechanisms, pathways, and understanding can help solve some of the problems that you may have with respect to catalysts or reactions at your end. And we have the expertise, and to perform these simulations, we have 5 million CPU hours per year to run these molecular simulations to understand mechanisms and pathways, which is about running 600 computers in parallel 24/7 for an entire year. I would like to stop here. Thank you, Isabella.
Thank you, Samir. I would now like to pass it on to Dr. Agree Morexi from the University of Calgary.
Thank you, Isabella, for the introduction. So my name is Agree Morexi from the Department of Mechanical Engineering here at the University of Calgary. Next slide. So our research is basically looking at system level analysis as well as component level design and optimization of low carbon energy systems. These are some of the systems that we are currently looking at. We are looking at systems for providing heating and cooling for buildings. That's the first system that is here, the direct expansion solar assisted heat pump system. Where this system works is that it uses the solar that is widely available to provide the heating instead of relying on ambient conditions that would make it less efficient. We're also looking at improving concentrating solar thermal technologies. These are technologies that can be used for process heat in industries. The challenge has been the costs that are involved in these systems, currently significantly higher than costs of energy from conventional systems. So we are looking at ways of optimizing them and bringing the cost down. Together with these systems, we are looking at energy storage because we believe energy storage has potential to increase the use of renewable energy sources and therefore reduce emissions. we're looking at a system for energy storage that can be coupled to a district heating network, and we are currently looking at using this for the Calgary district energy plant, which basically uses energy from renewable energy during the summer to store this one underground and then access it in the winter when it is cold and when it is needed. The other system we are looking at is compressed heat energy storage. This can be compared to pumped hydro energy storage systems or compressed air energy storage systems. The only advantage with this is that it can be used with a variety of renewable energy sources, and it can also use a number of heat sources, including solar thermal, waste heat from industry, as well as energy from depleted oil and gas wells, which we have in Alberta. We look at system level design and optimization of these systems, as well as techno-economic feasibilities of these systems. Next slide. These systems support the emission reduction goals of Alberta because for buildings, we know that about 13% of our emissions in Canada come from heating and water heating. Most of which comes from natural gas. So we are looking at systems that can have efficiencies between 400 and 600% and can also give you zero emissions if they are used with renewable energy electricity. We also looking at for solar thermal systems, reducing emissions from process heat, as well as electricity generation. And we are working with one startup that is looking at using some of these systems for process heat in petrochemical processing plants. The other system on solar energy we are looking at is generating hydrogen from natural gas by using solar thermal cracking. And that is work related to what Samir has just presented. But in our case, we are not using electricity, but we are concentrating solar energy to achieve high temperatures that can easily crack the methane into hydrogen and carbon, eliminating the CO2 completely from the system. For thermal energy storage, coupling the demand and supply for the intermittent renewable energy is one of the ways of increasing the penetration of renewable energy in our energy system. So we are looking at systems that we can use to store the energy from our system. Next slide. So the current scaling challenges for these systems have to do with the costs, which are still higher. So we are looking at technologies that can reduce these costs and make them cost competitive. We need to demonstrate these systems in our climates. And also some of the clogging that happens for catalytic conversion of natural gas is something we are looking at and trying to address. These are still new systems, like the compressed heat energy system is something that was proposed in 2014. So looking at sources and sinks for your energy is an important thing that we are looking at. And of course, industry and academia research partnerships are critical to success of the research that we are doing. Last slide. So what we are looking for from this is a field test site to demonstrate the technology performance in our climatic conditions, using these lessons that are learned to develop new components and systems to improve performance, as well as develop capacity for manufacturing systems at a component level from Alberta, therefore creating jobs and reducing the costs. Also looking for industry and research partnerships for us to leverage provincial and research and federal funding to fully develop these systems and utilize their full potential. Thank you.
Thank you, Agree. I would now like to turn it over to Dr. Xiao Lei Wang from the University of Alberta. Take it away. Oh, Xiao Lei, we can't hear you.
Sorry, I was muted. Okay, so hello everyone. I'm Xiao Lei. I'm from the Department of Chemical and Materials Engineering, U of A. And my research group mainly focuses on the design and development of advanced energy materials towards the clean energy technologies, including batteries, supercaps, and other electrocatalytic systems like water splitting or zinc air batteries. So As I just mentioned, actually everyone here pretty much very familiar with the sustainability. That's why we have this meeting here. And I don't need to emphasize the importance of the sustainability. So my research, since mainly revolves in batteries, we are really interested in how batteries can be contribute to the sustainability. And to us, we have two concerns, since batteries are believed to be clean energy technologies, and they are sustainable. But if you take a look at the batteries themselves, you can see actually battery contains a lot of components, including some of the elements that are not real sustainable. For example, we have the nickel, we have cobalt. They have negative environmental impact. And also, if you take a look at the process of fabricating batteries, we utilize a lot of organic solvents. We utilize this, some toxic solvents. We utilize some of the processes which are high energy consuming. So actually, in our opinion, how batteries can contribute to real sustainability involves in the three aspects, which are also our research focus. The first thing is the battery materials. So in our group, we mainly focus on the rational design of battery materials in terms of the functionality, specific morphology, or some of the structures, so that we can correlate their electrochemical performance with these factors. And we are also very interested in the efficient and cost-effective synthesis, particularly those processes which are believed to be green. And on the other hand, the second aspect is that we try to develop novel battery technologies beyond lithium batteries. For example, we focus on the lithium sulfur batteries. We focus on some of the aqueous batteries. Particularly, we work on the aqueous rechargeable zinc-ion batteries, which are very related to our topic today. And the very important aspect in our group is that how can we realize the circular economy by battery research? For example, if we can have battery recycled or upcycled, actually, in terms of those elements, we can reuse them, we can keep them in the closed loop so that we don't have to worry about if they are dumped to the environment. And also, if we can realize the recycling of battery technologies, we can significantly reduce the cost. So these are, we believe, the three solutions to the sustainable battery technologies. Because at current status, we believe that affordability and environmental penalty are the two major challenges for battery sustainability. So next page, please. Okay, thank you. So in my research group, what we mainly focus on is first the battery technology themselves, particularly zinc-ion batteries and supercaps, because zinc-ion batteries, also supercapacitors, have the same or similar battery structure to the current lithium batteries, the electrode, cathode, anode, and separator electrolyte, so that we combine them together to provide the energy to the external usage. So we focus on develop the materials, cathode and anode. We focus on the electrolyte. We focus on the whole setup, the configuration of these batteries. So in our group, for example, we make these battery technologies, the zinc-ion batteries, which can provide some of the desired properties, for example, the high capacity and the ultra fast charging. And I want to emphasize here is that we don't just do some very little coin cell button batteries for lab research. We make these pouch cells so that we can further increase the active materials loading or the electron loading to provide even higher energy of the batteries. And since we utilize some of the available materials, for example, we use carbon as the anode, we use polymer as the cathode, both of them are very cheap, so that we can make the batteries holding potential practical applications, holding the high potentials for practical applications. And the batteries that we fabricate in the lab can provide very high loading. Typically, we can realize the higher mass loading over 50 milligrams per centimeter square, which is much higher than that of the typical lithium batteries, for example, only 2 to 10 milligrams per centimeter square. And also these batteries can provide ultra long life, which can utilize can be cycled for over 1 million cycles. And of course, as I just mentioned, if you take a look at the materials that we use and our unique design and the materials, actually, we can also realize these battery applications in a wide temperature range from -60 to the room temperature or even higher to 60 degrees C. And the second solution is that the battery recycling I just mentioned. So we mainly focus on two things. One is the recycling of lithium batteries. For example, the lithium cathode plays a key role and takes most of the cost of the batteries. So we try to recycle the lithium cathode materials, and we try to regenerate these materials by two ways. One is that we leach the materials, particularly we try to recycle the lithium and the transition metals like cobalt and nickel, and then we precipitate them, and then we can make the lithium cathode materials again. Another way is that we try to regenerate them together by re-lithiation them, and by adding some of other additives, we can realize the cathode materials with even higher performance than the original spent lithium cathodes. Another very interesting topic is that we also try to recycle and upcycling other battery technologies, including the alkaline batteries, for example. Because for alkaline batteries, we utilize zinc as the cathode and manganese oxide as the anode. So the recycled zinc and manganese, if we assemble them, we can realize the rechargeable batteries even higher than some of the state-of-the-art battery technologies. And next page, please. Thank you. So the remaining challenge is, I just mentioned a little bit, because if you take a look at this figure here, we still have a long way to go to realize the practical use or commercial demands. And next page, please. So our expectation is that from the fundamental research point of view, we still want to explore different materials, we explore different possibilities. And for the practical applications, we would like to collaborate with our industry partners to leverage fundings from provincial or the federal agencies. We also would like to collaborate with our industry partner to see the real possibilities of commercializing these battery technologies or some of our recycling strategies. Thank you.
Thank you, Xiao Lei. Before we move on, I'd like to remind you all to put your research questions or comments in the Q&A function for our researchers. And with that, I will pass it on to Dr. Samira Sorianomi from the University of Calgary. Go ahead.
Thank you, Isabella. And hello, everyone. It's a pleasure for me to give this research presentation. And I'm Samira Sorianomi. I'm an associate of the University of Calgary. I'm going to talk about our U-Calgary startup company, just called Hyperox. And what we are interested in is a green and modular production of hydrogen peroxide. And the reason we are interested in hydrogen peroxide production, as you can see from this slide, is that it's one of the 100 top most important chemicals in the world. And it has the annual production around 6 million tons per year. And the current global market value is around $6 billion. The current largest scale production of hydrogen peroxide is through anthraquinone process, which is an energy demanding, large scale, multi-step hydrogenation and oxidation of anthraquinone. It requires central facilities, and it involves excess amount of organic solvents, which is not green. And on top of all of these, hydrogen peroxide that is produced needs to be transported to the place of use, which means GHG emission. It also places a safety issue because hydrogen peroxide is an unstable chemical, and it tends to dissociate rapidly. Now, our technology solves all of these issues. It's a zero emission, low cost, and modular production, on-site production of hydrogen peroxide. As you can see schematically here, we're using renewable electricity. Our only raw material is water. We are not using organic solvents here. We produce hydrogen peroxide and hydrogen, which can then be used for reduction of oxygen to hydrogen peroxide. And in fact, our technology produces, it's a two-sided production of hydrogen peroxide with 200% efficiency, and it's very useful for local applications. Next slide, please. Now, in terms of how this addresses the Alberta's emission reduction goals, it's a new technology, and it's based on electrochemical device, and it's modular, low cost, and with no waste, and there's no GHG emission in our technology, and it reduces the GHG emission for large facilities for hydrogen peroxide synthesis. One particular application of this technology, as you can see schematically here, is for solar wind distributed water disinfection system. but it's not limited to this application. It can be used for treating agricultural water and make it cleaner for agricultural products. Next slide, please. Now, in terms of our current challenges, we have this lab scale EChem cell, and as you can see, it works perfectly fine. And our current challenge is to make it large scale EChem and adapted this technology into a medium scale and then large scale EChem cell. This is an existing technology in Dr. Gates' lab, and we are transferring this technology to modular medium scale size EChem cell. This is showing on the bottom of this slide, we have the plan for the 2-year of the startup company. In the first year, we want to work on the continuous flow laboratory scale that takes 10 kilogram feet of water. And we want to refine our current IP for continuous reactor system. And we would like to engage in business development and establish partnership within Canada. In year 2, we want to scale up our technology to 1 ton per hour feet and refine our IP for large scale application and attract funding from Alberta Innovate. And we would like to, of course, examine market beyond Canada. Next slide, please. Okay, so in terms of our next steps, I definitely want to engage industry and investor network for partnership. Shown to the right is a table that compares our estimated price with HyperWorks, our startup company for production of hydrogen peroxide, compared to commercial values for a range of different concentration of hydrogen peroxide solution. And as you can see, our numbers are much lower than what is commercially the hydrogen peroxide is commercially available now. We are a strong team, consists of different material science with the skills and expertise in material science, reactor design, technology development, and scale up and commercialization. And our team also recently won the Horizon Prize from Royal Society of Chemistry. Move on to the next slide, please. So this is just briefly showing HyperWorks' current and future capacity. And as you can see, we currently produce a low value of hydrogen peroxide because we have a very small lab scale device, but it has a potential to produce 600 gram for the large scale commercial unit in 5 years. But this is the most exciting part of this, that shows the yield per year. This is per minute, of course, that's why it's small. But if you look at the yield production of hydrogen peroxide per year using our technology, you'd see that we will be able to compete with the hydrogen peroxide commercial producers at using this technology. Okay, that's all from me. Thank you so much for your attention.
Thank you, Samira. Over to you, Dr. Lindsay Sing from the University of Alberta.
Hey, can I have my first slide, my cover slide? Oh, I think that wasn't the first one, but okay, I think I'll get started. Hi everyone, this is Lindsay from Chemistry University of Alberta. So I'm running a research lab that specifically look at energy devices, next generation energy devices for green energy solutions. So our expertise is look at surfaces and interfaces in these multi-layer devices, and where we can look in depth in terms of the molecular level details while these devices are in operation. So this first slide shows that I'm trying to have our questions that asked by ERA listed on the left-hand side of the slide. So now we look at how this supports the Alberta emissions reduction goals, and basically we focuses on these devices that can solve the problem for sustainability and sustainable energy. So the ongoing project focuses on 2 types of devices: the solid state battery that can be safer and we can expect a higher energy density, or we can expect they store more energy, and some printable solar cells that can be likely wearable and can convert solar energy into electricity. And coming soon, we're also looking at a few other projects for example, materials that can absorb carbon, can actually capture carbon and the goal is to convert local carbon waste into high value component in next generation energy devices. So my lab look at these materials and devices, starting from the discovery of the material, the chemical synthesis, and the discussion of the structure of these materials, and correlate that into the performance of them in a real energy device. So we look at material discovery, we then fabricating and processing these devices into prototypes in battery and solar cell and other sensors. So we look at their performances, and most importantly, we have our expertise to do these cutting edge characterizations to really look down into molecular details when these devices are in operation. This is often called technology validation in industry, and we actually have our initiative. We actually started upon our little industrial initiative, and we're looking at looking for partners as well. Next slide, please. Oh, okay. So how this will fill a gap or solve a problem in industry. And in fact, we find that most of the time, the gap is actually the validation of the technology while you're actually pushing some sort of materials or technology into the market. So upon the 4 years that I come here in to the University of Alberta, we're actually building this LASI facility, the laboratory for advanced characterization of interfaces in energy devices. And this is actually funded by Canada Foundation of Innovation. And we have this full array of capabilities that starting from material discovery, the material synthesis, to environmental boxes, a couple of them, that we can do device prototyping, and to tools that you can do electrode deposition to make prototypes, and down to electrochemical working station that you would use to characterize the performance of the batteries and solar cells. And then most importantly, this center actually fund a few cutting edge characterization tools, and most of them are home built, right? And we're looking at molecular level details using advanced vibrational spectroscopy. And for example, the top one there, the specialized FTIR tools that we used for surface chemistry can help us to look at one single layer of molecule on top of a surface. And we use these tools for characterizations not only utilized in our energy devices, but we also use this to solve some problems that other industrial initiatives are care about. For example, one collaboration that we have would be look at sensor surfaces, molecules that use to modify the sensor surfaces that can help to actually solve some healthcare problems recently. Next slide, please. Okay, so we do have some current scaling challenges, and this shows one example of a project that we have that we try to have in industrial initiative in the next few years. So we start off from some ceramic solid electrolyte material that we discovered in the lab and try to develop processing tools so we can make them into thin solid electrolyte membranes, and in the future moving towards high energy stackable battery cells that can be used in electric vehicles and related market. So this is a project that is at its infant stage right now, and is funded by Alberta Innovates, and is right now in the process of the material processing and the solid electrolyte membrane development. And we're looking towards, in the next few years, build battery prototypes in the solid states and build stackable batteries, and then try to navigate with the industrial partners and look at properties that the industry really cares about. So next slide, please. Okay, so next step would be what we actually need from the pilot, and indeed it's the partnership. So we know everything about the material and the devices, and we do the characterizations, we understand the structure, we understand the performance, we also have a full array of validation for these devices and the material. However, what we really need is to understand in different applications what the real parameter or what the exact parameter that when this material is pushing into market would actually need. For example, when they're used in healthcare devices, what you really need would be a smaller size and the flexibility and the compatibility with biologic systems. Well, in a great storage system, the size is not really of a concern. Well, the amount of energy that can be stored would be of great concern. And in an EV system, the electric vehicle system, would so it will be somewhere in between. The size and the energy density would be very important. To have a partner within the industry would actually help us to provide us with the feedback so that we can start off with the application-oriented technology development. Okay, so I think that's my sharing here, and I would like to hear questions afterwards.
Thank you, Lindsay. We will now hear from Dr. Joanna Wong from the University of Calgary. Joanna, over to you.
Okay. Thank you, Isabella. Good morning, everyone. My name is Joanna Wong, and I'm assistant professor in the Department of Mechanical and Manufacturing Engineering at the University of Calgary. Today, I'd like to talk to you about one of the major focuses of my research in additive manufacturing of fiber reinforced polymer composites. So most of you are probably familiar with composite materials. You'll see them, you'll probably know them as fiberglass or carbon fiber. And these materials are highly used in lightweight applications such as the airplanes, as well as wind turbine blades. And they're also quite interesting for biomedical applications such as prosthetic lower limbs. Now, the issue with composite materials and composite processing is that they are, compared to other materials, highly expensive. This is due in part to the cost of the raw materials themselves. Carbon fiber currently sells for about $20 per pound or so. But when you actually go to purchase a composite part, an additional 80%, so $100 per, say, kilo, 80% of that cost is going to be in the processing. And the cost really comes from the dependency on the tooling, very expensive molds, and highly laborious processing methods. So one way we hope to make lightweighting technologies more accessible to different applications is to take advantage of additive manufacturing's ability to kind of circumvent the dependency on molds, or at least maybe reduce the dependency on molds, and therefore reduce the cost while increasing the design freedom capable. And therefore, well, then by allowing for this type of processing, we can then adapt more energy efficient designs by lowering the weight or increasing the functionality of certain structures. Next slide, please. Now, my lab is really looking at reducing waste and reducing energy from the whole manufacturing chain, from the raw materials to the preforms, to the actual manufacturing process, and then finally in the design of the structure. One example is when we're looking at the raw materials, we want to be sourcing from sustainable materials. I'm part of the Alberta Innovates Carbon Fiber Grand Challenge, where we're trying to take asphaltenes from Alberta and convert them into higher value carbon fiber products. Another thing we're looking at is the use of natural fibers such as flax or mycelium from fungus, and seeing how their properties and how they can be used to create a more sustainable composite material. Flax, for example, per weight, specific strength of weight, a specific strength of the flax fibers is on the same order of what can be achieved with fiberglass. I've also done some work on preforms, trying to reduce, currently composite processing is heavily dependent on expensive preforms such as pre-preg materials and autoclave processes, which are used for example, making the Boeing 787. And in order to bring composite materials to, say, larger mass manufactured markets, we really have to look into lowering the cycle time of composite manufacturing down to about less than 1 minute per part. So this involves manufacturing processes such as stamp forming, which requires new types and new approaches to developing preformed materials. Now, then I'm also looking at manufacturing, one of which is the additive manufacturing process. In the top kind of right-hand corner, you can see certain these lattice type beam structures, which are very, very difficult to make manually or with tools, with molds, but relatively easy to do using an additive manufacturing process. And these kind of lightweight beam structures can be used, for example, in bicycle frames or in deployable booms for satellites. And overall, by reducing this material use and the weight, we hope to also increase the performance and weight saving abilities of structures. Next slide, please. Okay. So the current challenges in additive manufacturing is really in achieving the material quality that you would expect from an end-use component. If you look at the square in the middle, where you see like a little purple highlighted region, this is a typical microscope image taken from an additive manufactured part using, say, a standard commercial process. Now, highlighted in purple in that slide is the voids of the material. So you can, on typical void content of a composite part that has been additively manufactured is easily in the 40 to 50% range. And there's very well-known correlations between the strength of a component and the void content. And so above, say, 2% of void content, the mechanical properties of a composite material will drastically decrease. The standard for aerospace components is less than 2% void. So you can see that there's a huge gap that we have to move from additive manufacturing quality down to what is acceptable for an end-use part. Now the image you see below, which is which also shows all the purple parts, but you can see that there's a huge reduction in the total void content. I think we're able to reduce this to about 4% using a patented in situ consolidation process. Another issue with additive manufacturing of composite materials is that additive manufacturing, as you know from like a maker, an Ultimaker system, is a layer by layer process, so that you're essentially depositing isotropic materials in a XY plane, moving up to the along the Z axis, and depositing it again. Now, when you're dealing with things like fiber reinforced polymers, these are anisotropic materials, and there is a certain advantage to being able to lay down the fibers along a load-bearing path. Now, these load-bearing paths might not necessarily be in that planar area, and so you would probably want to move it in and out of the plane along a surface, but the software is just not available today. Another issue is with the material selection, and my group is working not only in bringing aerospace grade qualities of materials to additive manufacturing, but also developing new ones such as carbon-carbon composites. Next slide, please. We'd love to start a partnership with local industry members in helping integrate the additive manufacturing process into a manufacturing line and incorporate sustainable materials in your products, as well as increase the functionality of your materials and structures. So thank you.
Thanks very much, Joanna. Over to Dr. Motada Sandra from the University of Alberta. Go ahead.
Thank you very much, Isabella. Hello, everyone. My name is Motada. I'm the lead of Advanced Model Research Lab, AWRL, at the U of A. Our mandate in the AWRL is to conduct research on the development of novel membrane materials and processes for water treatment and gas separation. Next slide, please. Membrane is a semi-permeable barrier that allows the passage of desired materials such as water and rejects the contaminants to pass through. Depending on the industry's needs, a certain membrane process is adopted. For industries that need to separate oil and bacteria from their water streams, microfiltration is suggested. For protein and virus separation, ultrafiltration membranes are used. For water softening, nanofiltration must be used. And finally, reverse osmosis is used for water desalination. Membranes can also be used for gas separation. For example, separation of hydrogen from syngas or separation of CO2 and H2S from methane. Finally, a novel application of membrane is harvesting energy from wastewater. For industries that need to treat low and high concentration of salt solutions at the same time, there is an opportunity to use pressure retarded osmosis, or PRO, to convert natural osmosis to electric power. Membrane processes benefit the industries as they provide high separation efficiency, can be easily scaled up and hybridized with other processes, and have a small footprint. That's very important for ERA. However, there are some challenges mainly related to the membrane material, which is the focus of our research in the AWRL. For water treatment membranes in the market, they have low thermal stability. For gas separation, current membranes provide low separation performance and are not mechanically strong. For energy harvesting, there is no specialty membrane on the shelf. Next slide, please. There are many industries that deal with high temperature process streams. Our thermally stable membranes have the potential to improve heat integration in these industries by conducting the water treatment at high temperature and preventing cooling and reheating requirements. For example, by replacing the conventional water treatment process in a steam-assisted gravity drainage, which is used for oil sands extraction in Alberta, with our thermally stable membranes, the GHG emissions can be reduced by almost 10%. In the case of biogas upgrading, the carbon intensity of the membrane process is as low as 36 gram equivalent CO2 per megajoule of the produced biogas. A rough estimation shows that replacing natural gas with biogas leads to a net emission reduction of about 40 million tons of equivalent CO2 per year. Finally, pressure retarded osmosis for energy harvesting is a renewable and green technology with zero carbon emission to the environment. In AWRL, we are manufacturing both flat sheet and hollow fiber membranes that can be used for both water treatment and gas separation applications. Can we go to the next slide? Next slide, please. We have already started manufacturing larger scale membrane and understand the current and future challenges. This video shows the third generation of our membrane manufacturing system. Using this system, we fabricate microfiltration and ultrafiltration membrane by casting a polymer solution, which is indeed our intellectual property. That casting solution will pour on the support. The process, next click, please, if you click once. The process, in fact, include casting, rolling, cutting, and trimming. The final product is the commercial scale 18-12-inch spiral wound module. The preliminary tests showed that this membrane can separate humic acid from wastewater by more than 90% rejection, and the flux is as high as 320 GFD. The technical challenges related to the casting solution formulation and manufacturing process design are already resolved in our lab. We predict some financial and logistic challenges for the mass production of these modules using a larger scale, fully automatic process. Next slide, please. The main risk for the successful deployment of our technology is the absence of a testing platform for the manufactured membrane. In the last 3 years, we designed and constructed emerging filtration setups for high temperature water treatment and energy harvesting from wastewater to mitigate this risk. Other risks that we anticipate are regulatory risks, for example, permit for field trial, budget-related risks for mass production and having higher scale manufacturing, and human resource risks. All these risks are important and of course are relevant, but we believe they are manageable by having some mitigation strategies in place. Thank you very much.
Thank you, Motada. And finally, our last researcher of the day, Dr. Michelle Dulgus from the University of Calgary. Go ahead.
Hi everyone. So my name is Michelle Dulgus and I am in the chemistry department at U of C, and we work on synthesizing and characterizing new piezoelectric materials for different energy related applications. Next slide. So first, for anyone who's not familiar with the piezoelectric, it converts between mechanical and electrical energy and vice versa. So you can either apply a force and it generates an electric field, and in that case, it can be used as a sensor, so something that detects changes in the physical environment, so like a pressure sensor, gas sensor, accelerometer, and things like that. And then that's also reversible. So you can apply an electric field and then the material will actually physically distort. So in that case, it's used in actuator applications where it converts that electrical signal into a precisely controlled physical displacement. It's used to control hydraulic valves, small volume pumps, kind of special purpose motors that require precise movements and things like that. And then it can also be used as a transducer device, which actually does the conversion between mechanical and electrical energy. And then that's used in ultrasonic imaging, strain gauges that measure force, stress, vibration, and things like that. Next slide, please. So for the challenges in this space is that the industry standard piezoelectric, it contains lead, which is toxic to the environment, and it also has a low operating temperature. So it can't be used really above 100 degrees Celsius. But one of the challenges is that the piezoelectric response, so how well it responds to the stimuli, is inversely proportional to its maximum operating temperature. So we've worked in two spaces here. So we're looking at thin films, and we've been able to synthesize a thin film material that we've developed this environmentally friendly synthesis technique using aqueous solution. And that the precursor solution, as well as the synthesis technique, we're in the process of the full patent application for that right now. That particular material does not have any lead in it, and it also works at a higher temperature than the industry standard. And this thin film material can be used, because it doesn't have lead, it has the possibility to be used in vivo, so in a biomedical device like a pacemaker, where it can detect the level of physical activity. So then that device can be adjusted as needed. It can also be used as an ultrasonic sensor, and then a vibrational energy harvester. We've also synthesized a novel ceramic piezoelectric material that we're in the process of applying for a provisional patent for. And this material, it has a higher operating temperature of about 600 degrees C. And you can see on the plot that our ceramic has a larger response, so it's more sensitive than other materials that have that similar maximum operating temperature. So this ceramic can be used in things like structural health monitoring at high temperatures, a sensor at high temperatures, and anything really that's used at elevated temperatures that also need high power transduction applications. Next slide, please. So the ways that this supports Alberta's emission reduction goals is that we've been able to come up with an environmentally friendly synthesis technique for our thin film. So it's synthesized at lower temperatures, and also for the annealing time goes from an hour to about a minute. So we have significantly reduced energy needs to make these thin films. And then generally when you do solution processing of thin films like we are here, you use nasty organic solvents, but we've been able to do this using aqueous solution chemistry. So there's no waste really. For both the thin film and ceramic materials, this could be used as an energy harvesting device, which is really cool. So these, like at a train station in Tokyo, the tiles are lined with piezoelectric devices. So every time you step on it, it creates an electric field, and then they can then save that energy and store it for use in the lighting in the train station or something like that. And then it can also be used for sensing in like manufacturing facilities. So any type of manufacturing facilities, it can be used for sensing at higher temperatures. Next slide, please. So some of the challenges for this, for the thin film material is scale up. So right now we do spin coating, and we just use this tiny little spin coater that fits in the hood of our lab. But in order to scale up, we likely need to do something like spray coating, and that requires equipment that we don't have access to. I don't think there's anything here at Calgary. And then for the thin film and ceramic material, we're looking at adding small amounts of different types of atoms to try to tune the material and optimize the properties. And I think in both the thin film and the ceramic, we're kind of at a point where it's beyond fundamental research, because we're trying to figure out how it can actually be used in optimizing properties, but it's not quite ready to be like a startup or something yet. And that's an area where funding can be difficult to find when you're in between like fundamental and then like starting a company with something. So that's a little challenging as well. And that's for both these materials that we're working on. Next slide, please. And then just as a side note, my group has world-class expertise in structural characterization. So we can look at everything from amorphous materials to crystalline materials. We've looked at semiconductors, battery materials. We can do in situ and in operando structural characterization. So looking how the structure changes as a function of electric field. We can do in operando battery measurements, where we look at how the structure changes for charging and discharging a battery material. And I just wanted to mention this because this is something we would be interested in either consulting or collaborating with others with. I think it's really important if you have a material and you're trying to understand the properties or change the properties to tune something for a specific application, a good way to understand the direction that you need to go in is to understand the atomic structure. And that's something that my group is highly, like we have high expertise in this area. So this is something that we like to work with people on collaborations with as well. And that's all I have. Thank you.
Great, thanks, Michelle. And thanks to all of our researchers, especially for staying on time. I know that there's a lot to cover and we haven't even scratched the surface. So thanks again. It's very exciting to see the potential in all of these research areas and in what you're researching and what you're doing. The intent of this session is to connect these research areas and the expertise with those working in industry to see where the possibilities may lie. So I don't want to say too much more here. I'll open the floor now for some audience questions or comments. Again, you feel free to add questions to the Q&A feature or raise your hand so that we can find you. Now, we want to ensure we remain respectful to all those on the call and enable a productive and fruitful conversation. So if you are comfortable and would like to turn on your camera when you ask a question or pose your comment, please do so. I will ask all of our researchers to turn their cameras on so that we can all see your faces. And I know that it can take a couple of minutes for some of these questions to be ready here. So maybe I'll just pose a few to get the conversation going. Researchers, I'm going to ask these questions of our audience for them to think about, and perhaps you can layer in as you see it relates to your work. But for those participating in the session, I want you to think about if there was a project here that you could see that has a direct application to your organization or line of work. Feel free to chime in or jump in with what you would like to see or where you would like to see that applied. And if there's any work here that you want to hear more about as it moves through the research phases, I'd like you to also think about that as well. While you gather your thoughts, I'm going to pose a question to each of our researchers in hopes that you can answer this in about a minute or less. What are some of the lessons that you've learned throughout your research careers? And if you can give us a little sense sense about, some of the barriers that you faced, or some of those sort of key, brilliant barriers that you've had to overcome and you'd wish you'd sort of known when you first started this research. And maybe we'll start with Joanna. Over to you.
Well, I think one of the things that I've found is that as researchers, we think we know what the problem is, and then you go and you talk to industry, and like their problem and their issues is completely different than what you expected. So often, like we're very interested in. So I work with thermoplastic polymers and composites, and we're interested in the recycling and such. Whereas when we go and talk to an industry member, they're really into cost reduction and manufacturing and how to keep manufacturing, say, local. So there's just different issues that we don't consider as much as researchers that we'd like input on from industry.
Thanks, Joanna. Motada, over to you.
So I agree with Joanna. Yeah, the main problem that we have to secure funding from industry is that we don't understand maybe the main problem in the industry. So they're dealing with the different sort of problems, not mostly requires fundamental research. Some of them needs quick action, practical research. We need, for example, in my research area, they need membrane of a larger scale. Yes, I can make flat sheet membrane in a lab, which is very good. It works very good in the lab scale, but they say actually that we have a facility in Fort Mac, we want to run it in that facility, for example. So you should go for a larger scale. And I changed the direction of my research over time in the last 7 years to meet the requirement of industry. So every one of us should have some flexibility, industry, government, university. So I had this flexibility to make larger scale membrane, which may not be the mission of university at all.
Great, thanks, Mo. Samir, go ahead.
Yeah, I agree to what Motada and Joanna said. And also, I think one of the things that we face problems in my research group particularly, because when we talk about these catalysts and modifications that we suggest, so these are done using very high-level quantum mechanical simulations that are run on supercomputing facilities, and we come up with these suggestions. And it's really difficult to convince that, yes, these are simulations, but indeed this material can be synthesized and does exist in reality. And we have shown that in a few cases where either we ourselves or our collaborators eventually tried and were able to synthesize and found it out that yes, this material does exist. For example, we had a material which was copper and boron, which don't mix with each other. They don't form an alloy. But then there's a certain microstructure where they do come together, and that enhances the activity of copper to the next level. So, so I think it's a challenge to convince that these kind of simulation and computational work also can help and make a big difference, because otherwise just trying and testing different catalysts and experiments may not give you the result that you're looking for.
Yeah, great points. Thanks, Samir. Agree, what are your thoughts?
Yeah, just like the previous speaker said, technology development can be quite expensive, and at early stages, when you're still trying to figure out how your technology works, how your system operates, you're mostly looking at theoretical analysis, you're looking at modeling, and in most cases that might not be of interest to industry. Industry is looking for maybe something that is ready to go, that would be cost competitive and cost effective to implement in their processes. So getting that funding to do the initial studies until the technology becomes cost competitive can be a challenge.
Thanks, Agree. Lindsay.
Right, so I agree with what everybody just said. I just want to add one point. I did find it difficult, or there is at least a mismatch much of what we care about as a researcher in terms of fundamental research, in terms of how we support our student to get their degree, and what the industry actually cares about in terms of making a real product that can be commercialized, can make money, or can be the future in the community. But what I found was sometimes industry, or especially the initiatives or the startup companies, also really need the validation of the technology. And as one example that, as at the beginning, while in the process of applying for a patent or getting one product or one device that's ready for the market, you need to convince the audience, you need to convince the community that this technology actually works, and you understand every single detail aspects within how it works. If there are there are performance that is not quite ideal, you understand what that is, and in terms of fundamentals, and you understand how to modify that. So I found collaborators or industrial partners come to us, trying to find the answers to those questions. So I don't know if that's where we find where that mismatch really is. But I think it's a good sign to add to all the comments that we heard from the previous speakers.
Yeah, thanks, Lindsay. The importance of partnerships, I think, rings true in our ear as well. Over to you, Samira.
Yeah, so I kind of agree with all the points made by the other colleagues. I think one additional point I can add is finding partnership with industry is quite difficult for us, especially as early careers. Excuse me. And I think that these events that you organize, it's really useful to kind of see that connection and find the partnership, especially for us that we're looking for partnership with industry and companies that support our ideas and technology that we develop. So I think it's those kind of connections and meetings are pretty much unique and rare, I would say. So I really found it challenging to find industry partners.
Thanks, Samira. Xiao Lei, any thoughts to add on some lessons that you've learned over the years, or any key barriers that you're currently facing?
Oh, thank you. I'm sorry for missing some of the parts because I had another meeting to go. And yeah, I'm so happy to have this chance to talk to or to show our research progress to our industry partners. And the challenges that we found is mainly the large barrier between our fundamental research and the practical applications. And also, actually, from our side, actually, we don't quite understand some of the processes, some of the demands from the industries, and I believe from the industry partners, they are not familiar with some of our work. So, I mean, this platform is very useful for us to show our work and to build some of the connections with the industrial partners. And also, what I like from this kind of conversation is that we can have some possibility to collaborate with our industry partners to, for example, to leverage some of the fundings from provincial and fundamental government agencies. And also, it's also a good opportunity for us to invite our industry partners to visit our labs or groups so that we can show some of our recent progress to the partners, so that we can have more communications and we can show the details. We can let our industry partners know what we are doing and what would be the possibilities to commercialize or at least to scale up some of our technologies or strategies.
Thanks, Xiao Lei. And finally, Michelle, last thoughts.
Yeah, I guess my big thing about this is that I think there's a huge gap in funding opportunities between the fundamental research and then being ready at the point where you're ready to either license out your technology or create a startup on your own. You know, if you just want to tune properties or optimize something, that doesn't seem always appear to be a big enough impact for fundamental research, but then you've not been able to demonstrate that the material has the properties that a company needs or anything. So there's that kind of giant gap in the middle where you really are like, oh, I just made this new thing, I think it could be great. And you just want to really kind of accelerate that research to try to get it to the point where you can license out the technology. I think that's kind of a big challenge.
Awesome, thanks, Michelle. We have a couple questions here in the chat. The first one I will address in terms of the slides and contact information. Yes, everything will be made available to our participants after this webinar, so stay tuned for that. We did have another question here come in just on the state of the industry so far, and maybe if each of the researchers could talk about the industries that you're targeting and how these industries have changed in terms of demand that you're seeing for the research that you're working on. Maybe you can give participants a little bit of that in terms of how it fits some of the long-term, short-term goals and strategies of some of these industry players. And Samira, we'll start with you.
Yeah, so that's a very good question. I've been thinking about this for quite some time. I think there's a hydrogen, currently we have a hydrogen peroxide facility in Alberta, and I think it would be a very good partner for our technology, because our technology is zero emission that can kind of solve some of the GHG emission related problems, and also with the distribution of hydrogen peroxide, because we don't know how we can distribute our product. So they would be very good partners in terms of helping us through that process to find market for our product. I also think that companies that are dealing with water treatment and agriculture would be a target for our technology, and very good partners. So these are companies that we think would be relevant. I don't have any particular name in mind, so I would really appreciate if those companies can connect to us, and we can take it from there.
Thanks, Samira. How about over to you, Lindsay?
So I'm just making some notes and thinking about the list of companies that I would be interested in talking to. So first of all, I think, of course, it's a lithium battery and related metal battery technology, and companies within the area. And I found we don't really have a lot in the western of the country, and usually it's mainly more concentrated in the center, in the eastern part of the country, and Ontario area. Companies included doing work in terms of lithium extraction or general battery companies that this is the first thing that we would like to talk to, because we are developing this membrane material that can be used as part of the solid state battery system. And we hope that we understand all the aspects that the customer and the industry is interested in, so that we have a targeted development, even starting at the infant state. And we are also interested in talking to sensor companies and materials companies, especially for carbon conversion and carbon reuse, because we have this cutting edge surface characterization center that we think that we can actually do a lot of things that other people in the country cannot do. And we can look very, very specifically on the device itself that can answer lots of questions in terms of how to improve the technology, how to modify the device, and how to make it, cut the need. So yeah, that's sort of the two types of companies and industrial partners we're looking for at the moment.
Thanks, Lindsay. Over to you, Xiao Lei. We'll give Xiao Lei a couple seconds. Maybe when if Xiao Lei's gathering his thoughts, we'll go to you, Michelle.
Okay. Yeah, so I guess for me, it would just be things like sensor companies, and especially now with like the Internet of Things getting to be a big thing, and there's sensors on everything. That's something that we're interested in looking at, manufacturing facilities and places like that. And I guess like one thing, like piezoelectric materials are essentially in almost every electronic device. So when you do find something interesting, I've taken courses and training to do market analysis and understand how to, look for where your product might be, where it could be actually useful and used in real life applications. But with piezoelectrics, there's just so many. So trying to, find that perfect application is something that can be challenging too.
Thanks, Michelle. Agree, any thoughts?
Yeah, so for most of the work that we do, it is applicable to companies in the energy sector, especially utility companies that are looking for energy storage solutions, both for electricity on a large scale, as well as thermal energy storage. We also do work on simple systems for residential applications, so heat pump systems for electrification of heating. And this could be used by property developers, or they could be things like utility companies could look at if they want to reduce the burden on the grid or investments in the grid. And also heavy manufacturing industries where they have process heat that can be supplied by solar thermal, or that can be used, waste heat that can be recovered and used to couple with thermal energy storage systems.
Thanks, Agree. Motada, go ahead.
Thank you, Isabella. As you notice, the main receptor of my technology, membrane technology, currently is oil sands industry in Alberta. But we know that Canada is the main, one of the main exporters of the food and wood industries, like material. And in all of these industries, water treatment is an issue, and water treatment can be used for residential wastewater treatment as well. But you may say that we have different types of membrane in the market, and I had this in my presentation, that we are targeting some niche applications, some, for example, high temperature wastewater treatment or energy harvesting for wastewater treatment, that we don't have any membrane on the market, on the shelf for such applications. So I can say that we should also consider that what is our competitive advantage compared to the companies that are currently producing membranes. Ours is high temperature, biogas upgrading, a specialty membrane, and of course, membranes for energy harvest.
Thanks, Mo. Joanna, over to you.
Okay, so in the composites industry, we're mainly driven by like very conservative industries like aerospace and automotive. And so to introduce new materials and new processes, it requires a whole sense of like lengthy testing. Standard testing is particularly difficult, especially when you want to look at new materials like thermoplastic polymers, which experience creep. These structures, airplane structures, wind turbines are expected to last 40 years, and these industries really need to know how is that structure going to behave at the end of 40 years. And also, it's particularly with recycled materials. It's one thing to recycle a PET bottle and turn it into another PET bottle, but when you start recycling carbon fiber reinforced materials, every processing step chops down that material, degrades it slightly, and we just don't know enough about the degradation of that material. And so before we're able to move new materials into this industry, we have to put up a whole new set of standards.
Thanks, Joanna. And Samir, finally over to you.
Thanks, Isabella. So I'll talk about two things. One is the hydrogen production, and the other is the biofuel sector. I mean, I think with respect to hydrogen production in last 1.5 years, what we have seen is all these big industries that are making investments, particularly in Alberta. But I don't know, I mean, other than what we read in newspapers and magazines and stuff about their investments, and then they're coming up, setting up plants, we don't really know, to be honest, much if it's going to be still conventional steam methane reforming, or are they interested in looking for new technologies with respect to this. I think it will be very nice if we get to know a bit more, or at least if we get to know that they're interested in anything like that. With respect to the biofuel sector, I mean, this was a little research that I did some time back, and I figured out that in last 10 plus years, governments in Canada have invested about $2.5 billion in biofuel research, but we have not moved beyond bioethanol, food crop ethanol, and biodiesel. This bio oil that we talk about, probably there is one or two companies, and quite a few started and then they shut down, went bankrupt. Even in Europe, where they have some big plants for bio oil production, the best they get is 20% yield, which means 80% of the carbon that you get from biomass is basically lost. So, and that's why this will never become commercially feasible. And, so in terms of this bio oil industry, for them to become commercially, economically viable, I think the big challenge is that the yield of bio oil and the quality at the same time has to be much higher than about 15%, 20%. And again, whatever commercial plants are there even in Europe, they are right next to some the resource where this biomass or lignocellulosic biomass is produced. They can't be decentralized. So, so I think some work in that aspect is needed if we have to go anywhere with respect to biofuel.
Thanks, Samir. So just on to our last question here, and I'm just going to pose this to all of our researchers before we wrap up, just something a little bit fun that we've never done before. And I would say in about 5 to 10 words or less, why should industries reach out to you? Why should they be excited about your research? Why are you excited about your research? And what is sort of gravitating you towards continuing this research? Why do you think it's important? Just anything that will excite us, other than all of the great things that we've heard today. And Agree, maybe I'll start with you.
Yeah, so for the research that we do, we're looking at helping families address the energy-related emissions problems by looking at new heat pump systems, for example. We are looking at low carbon technologies, so significantly reducing the emissions from the energy we use for heating, for domestic hot water heating, and also storing this energy and using it when it is not available. So we do a lot of work on energy storage, thermal energy storage especially, and we think and believe that as the integration of renewable energy into our electricity system goes on, we need to capture this energy and store it when it is available and use it when it is not available. So it is exciting work to look at these kinds of systems.
Thanks, I agree. Rapid fire, Samir, over to you.
So I'll answer the first part, that why I am excited about it. I think one of the big reasons is, it's more, a lot of times it's a lot of curiosity-driven research, that you don't understand how things are happening, why they are happening, and you try to find out those answers, which I think is something that I really love. And also to see if we can improve on what exists, right? How can we do better? So that kind of are the things that kind of drive me. Now, why industry should be interested? I think, I'm not sure if I can answer that, but if I can speculate, that is one that, if they are looking at, if they're looking at something that can make a big difference in long term, may not be next 6 months or 1 year, which is also possible if it's very applied, or if the TRL level of what we are doing is quite high up there. But otherwise also, if it's a game-changing kind of thing that can happen with what we are trying to do in a relatively longer period, that would be great. And also, I think one of the things that we are also missing is it's quite possible that with industry, everything that they are doing, they have some problems about which we have absolutely no clue. And it's possible that we have the tools to solve them, but they don't know if we have those tools. So even without them telling the problems that they have, if there is a way we can convey to the industry that these are the tools that we possess, then that will help them realize, oh, by the way, this is the guy that probably can solve some of my problems that I have. So it's not only about we want to do research and commercialize and then take their help, but if they have something already commercialized, but if they can make a 5%, 10% improvement, that can make a big difference to them. And, we help them. That's a two-way traffic then. But, so.
Great. Thank you, Samir. Over to you, Michelle. Just a couple quick words before we close.
Yeah, so I'm just really excited, especially about our ceramic material, because it's very clear that our material has a better piezoelectric response than any other material with similar maximum operating temperatures. So this is a new material. We've synthesized it in our lab. I've been trying to do this for 12 years, and I finally did it. So I'm really excited, and I think it could actually be something. So
thanks, Michelle. Joanna.
I think I counted like still less than 10 words. I was thinking that the research I do has a technological and economic impact through the cheap manufacturing of energy efficient, lightweight, high performance structures. We don't create sustainable energy, but we do try to extend and expand the energy we do have through the use of efficient structures, lightweight.
Thanks, Joanna. Motada.
A very difficult question, I can say, but I usually, when I talk to my students, I tell them that there are some research areas in my group that keep me awake. And I want to know what will happen next day. So one of them is energy harvesting from wastewater by different methods. It can be pressure retarded osmosis. It can be using piezoelectric materials that uses actually the pressure fluctuation. Other types of the energy harvesting, like thermo-osmotic energy conversion, that you are using a waste to make added value product. Another research area that I'm really interested in is, again, actually creating wealth from waste or byproducts. It's lignin, for example, is one of them, using lignin to make membranes. So why just using a polymer, which is precious, to make membrane? Using something which is not valuable is a problem of another company, and make added value product is another research area that I'm interested. Precious metal recovery from brine, like lithium extraction from brine. We don't have actually unlimited reserves of lithium or cobalt, and we can use it in Alberta. We can recover lithium in Alberta, and that's it from me.
Thanks, Motada. Xiao Lei, over to you. Quick words.
Okay, thank you. And the first question, why I'm excited to the research, is most from the fundamental research point of view. Actually, we are working on some new areas. We are doing some, we are trying to advance knowledge in the certain fields. And the second question, why the industry partners reach us actually is more important, because what we are doing is also useful, because we are in engineering. And for example, I introduced the two technologies today. One is the zinc iron batteries. You can see that we have these high performance zinc iron batteries. They are cheap, they are safe. Although we don't expect they replace the current lithium batteries, but actually we offer the market more choices. And the next thing is the battery recycling and battery upcycling. Actually, this is a very interesting and very new area for the current battery technologies, not the traditional ones. And we try to make a cheap process. We try to contribute to the sustainability, to the environmental benignity aspect, so that we are making some effort in this area. And these are really useful, and these are really practical, applicable in the market and for industry partners.
Thank you. Lindsay, quick words, over to you.
Okay, so 3 questions. First, our excitement. Of course, the clean energy, I was excited about molecules for many, many years. I was actually excited about the new structures and new materials. But now with this new role, I'm really excited to see, the whole world it's actually very excited about the clean energy industry, and it's a multi-billion industry. So I think the research will not only create opportunities within Alberta, it also can at some point absorb investment from outside of Alberta and actually from international places if all of us are actually working together. And the second question, why industry could find its way to contact us and do some work together. I think our expertise in technology validation, especially in solid state devices and electrical devices validation, would be very valuable. And my students were quite creative in terms of understanding the chemistry behind a device and how to improve that. And the third is actually my hope or my dream in terms of holding our HQPs around, right? If the industry and the post-secondary institution can actually work together and support financially and intellectually support our HQPs and our students around, even after their graduation, it will be tremendously helpful for our transition from an old style, energy system in transition that to a new sustainable energy system. Unfortunately, I saw so many students, good chemists and good material scientists moving out of us, although they like to stay, but they're actually moving out of Alberta because we cannot offer opportunities in this battery and new clean energy industry. We don't have a good enough such industry within our province. I think we should all work together towards that goal.
Thank you, Lindsay. And finally, Samira.
Yeah, thank you so much. I think just a few words. I'm very excited about this research. In my group, we develop materials for many different applications. Hydrogen peroxide synthesis is on top of our research interest, because hydrogen peroxide is one of the most important chemicals. So the current pandemic situation, we need it more than ever. And our technology helps to make it sustainable and more accessible to the people who need hydrogen peroxide for many different applications, including sanitization and water treatment.
Thank you, Samira. I just want to thank you all for the active participation and great discussion. And thanks to those who made this session possible. A special thank you to our CEO, Steve McDonald, for kicking off the session. Before we close, I'd like to take a quick moment to acknowledge Dr. Ann Nath, Director of Energy Systems and Director of Future Energy Systems at the University of Alberta, and Dr. Ian Gates, Director of the Global Research Initiative for Sustainable Low Carbon Unconventional Resources from the University of Calgary. Thank you so much for working with us to make this session happen and bringing this work to our attention. As mentioned, we will be sending around a package to all of the attendees, which will include a brief one-page summary of each research area, as well as contact details for each of the researchers today. We will also be including additional communications on our website and potentially in our newsletter, so stay tuned for that. Again, thank you for joining us, and I hope you all have a wonderful day.